Good evening and welcome. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. Tonight I want to ask you something simple. Look up. Not now, but in your memory. Think of the last time you stood beneath a sky so full of stars, you forgot where you were standing. Did you ever wonder how far those lights had traveled just to meet your eyes? Did you ever try to imagine the distance you couldn't? None of us can. And that's not a failure of imagination. It's something deeper. Something about the way our minds were built. Before we drift into this quiet journey together, if you find comfort in these stories, told softly, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more nights like this, and ring the little bell, not for noise, but so the next quiet night can find you again. It means more than you know. Now, let's drift. Tonight we're going to talk about light years. Not the way textbooks explain them, not with numbers that mean nothing, but the way they actually feel, the way they stretch time, break intuition, and turn distance into something closer to dreaming than measuring. Because here's the truth most people don't tell you. A light year isn't really about light. It's about loneliness. It's about the space between things. It's about how far you'd have to travel before you'd ever arrive. And once you understand that the universe starts to feel different, quieter, older, more impossible than you thought, you don't need to understand everything. Just rest and let curiosity do the listening. Let's begin with something small, something we think we know. The sun. Right now, as you hear these words, the sun is shining. Or at least it was. 8 minutes and 20 seconds ago. That's how long it takes for light to travel from the surface of the sun to the surface of the earth. 93 million miles crossed in the time it takes to boil water for tea. Scientists call this an astronomical unit, 1 AU. It's the baseline, the first rung on a ladder that reaches farther than anything else we've ever tried to measure. But 8 minutes is strange, isn't it? It means that if the sun disappeared right now, simply blinked out of existence, you wouldn't know. Not yet. For 8 minutes and 20 seconds, the sky would still be bright. Birds would still sing. Shadows would still fall. You'd be living in a world that no longer existed, and you wouldn't feel a thing. That's what distance does at the speed of light. It turns the present into the past. It makes now a memory before it even arrives. And 8 minutes is nothing. It's the shortest distance we'll talk about tonight. Because once you leave the sun behind, once you step beyond the edges of our solar system, the numbers stop making sense. Let me show you what I mean. In 1676, a Danish astronomer named Ole Rømer was studying the moons of Jupiter. He noticed something odd, the eclipses of Io. One of Jupiter's moons didn't happen on time. Sometimes they were early, sometimes late, not by much. Just a few minutes here and there. Rømer realized something no one had proven before: light wasn't instant. It had a speed. And the reason the eclipses seemed to drift was because Earth was moving. When Earth was closer to Jupiter, the light arrived sooner. When Earth was farther away, it took longer. It was the first time anyone had measured the speed of light. Not perfectly. Rømer's estimate was a bit slow, but he was close enough to change everything. Because once you know light has a speed, you can start measuring the universe with it. You can ask, how far does light travel in a year? The answer is 5.88 trillion miles. That's 1 light year. But let's be honest, that number doesn't mean anything to you. It doesn't mean anything to me either. Our brains weren't built for trillions. We're good at tens, maybe hundreds. 1,000 if we're really paying attention, but trillions. That's just noise. So let me give you a different picture. Imagine you're driving a car, a fast car, 60 miles per hour, straight ahead, no stops. You drive for an hour, then another, then another. You drive for a full year, 365 days. No sleep, no food, just driving. At the end of that year, you will have traveled about 500,000 miles. That's impressive. That's enough to circle the Earth 20 times. But to travel 1 light year at that speed, you would have to keep driving for 10 million years. 10 million years. That's longer than our species has existed. That's longer than most species have existed. You'd start driving before the first human stood upright, and you still wouldn't arrive. And that's just 1 light year. The nearest star to Earth, not the Sun, but the next one is 4.24 light years away. That's Proxima Centauri, the closest neighbor we have in the entire universe. And it would take you 40 million years of driving to reach it. Do you feel it yet? That small, quiet vertigo. That sense that distance isn't what you thought it was. This is where most explanations stop. They give you the numbers, they tell you light years are big, and then they move on. But I want to stay here a moment longer, because there's something else happening. Something about the way our minds try to hold these distances and fail. Psychologists have studied this. There's a concept called number sense. It's the brain's ability to estimate magnitude, to feel the difference between quantities. And it works beautifully for small numbers. Show someone 3 dots and 7 dots, and they'll know instantly which is more. But once numbers get large, something breaks. Researchers at MIT found that when people are asked to compare 1 million and 1 billion, most people know the billion is bigger. But they don't feel the difference. Not really. 1 million seconds is 11 days. 1 billion seconds is 31 years. That's the difference. And yet in our minds, they both just feel like a lot. Light years do the same thing. 4 light years, 400 light years, 4,000 light years. They all collapse into the same feeling, far, unreachable, impossible. And maybe that's okay. Maybe the universe isn't asking us to understand it, just to witness it, to let the scales sit quietly in the back of our thoughts like a dark ocean we'll never finish crossing. But here's where it gets stranger. A light year isn't just distance, it's time. When you look at a star 4 light years away, you're not seeing it as it is. You're seeing it as it was, 4 years ago. The light that touches your eyes tonight left that star before you started reading this sentence, before you woke up this morning, before last winter ended. Every star you see is a ghost, a memory of something that might not even exist anymore. And the farther you look, the older the memory becomes. The North Star Polaris is 323 light years away. The light you see tonight left that star in the year 1701. When that light began its journey, Isaac Newton had just published his work on calculus. The first piano had just been invented. Most of the world had never heard of electricity. That light has been traveling alone through empty space for longer than your great-great-great-great-grandparents lived. And tonight, by accident, by pure chance, it arrived at your eye. You are watching the past, not a recording of it, the actual past. Still traveling, still arriving. Doesn't that change things? Just a little, I think it does. I think it makes the night sky feel less like a place and more like a kind of time machine. A museum of light, a library of old stories written in photons waiting to be read. And we haven't even left our neighborhood yet. We're still talking about nearby stars, stars you could point to if you knew where to look. But the universe is so much larger than that, so much older. And the distances we've been measuring, these light years, these trillions of miles, they're just the beginning. Because soon we'll need to talk about what happens when distance becomes so great it stops feeling like distance at all. When space itself starts to stretch. When the light we see isn't just old, it's impossibly old. Light from a time before planets, before stars, before anything we would recognize as a universe. But we're not there yet, not tonight. Right now, we're still here, still holding on to something we can almost imagine. A star 4 light years away. A beam of light 8 minutes old. A distance measured not in miles, but in time. And maybe that's enough for now, to sit with that feeling, to let it settle, to realize that every time you look up, you're not just seeing space. You're seeing history, deep history. Light that left its home long before you were born and arrived just in time to meet you. Isn't that strange? Isn't that beautiful? The stars didn't know you'd be here, but you are. And they've been traveling all this time just to reach you. So, before we move deeper into the dark, before we start counting distances that don't make sense anymore, I want you to remember this. The universe is not asking you to comprehend it. It's asking you to feel it, to let the impossible numbers wash over you like a wave, to let distance become something softer, something closer to awe. Because that's what a light year really is. Not a unit of measurement, but a reminder that we are small and the universe is patient and light travels farther than we'll ever go, and still somehow it finds us. We've only just begun to understand what distance means when light becomes the ruler, but already something shifts. The stars feel farther, time feels slower, and the night becomes a little more gentle knowing how long those photons have traveled just to meet your tired eyes. Let's keep drifting now, deeper into the strange mathematics of measuring the unmeasurable, where the first humans who dared to count the stars discovered something both terrifying and beautiful. There was a time when no one knew how far the stars were. Not approximately, not even close. They were just lights, beautiful, unreachable, and utterly mysterious. For thousands of years, humans looked up and wondered, are the stars just beyond the clouds? Are they holes in the sky? Are they painted on some great celestial sphere that turns above us while we sleep? The ancient Greeks tried to measure them. They failed. The Romans tried. They failed too. For most of human history, the stars remained exactly what they appeared to be. Distant, yes, but how distant no one could say. And then slowly someone figured it out. Not all at once, not with a single breakthrough, but piece by piece over centuries, a handful of curious minds built the ruler we now use to measure infinity. This is the story of how we learned to count light. Let's go back, way back, to the year 280 BC. A Greek astronomer named Aristarchus of Samos stood on the island of Samos and did something no one had done before. He tried to calculate the distance to the sun. His method was clever, brilliantly clever actually. He observed the moon during a half-moon phase when exactly half of it was illuminated. He realized that at that moment, the sun, the earth, and the moon formed a right triangle. And if he could measure the angle between the earth and the sun from his position, he could use geometry to calculate the distance. His tools were primitive. No telescopes, no computers, just his eyes, a stick, and the shadow it cast. His final estimate was wildly wrong. He calculated the sun was about 19 times farther from Earth than the moon. The real number is closer to 400. But here's the thing he tried. He was the first person in recorded history to treat the cosmos not as a mystery to worship, but as a problem to solve. He looked at the sky and said, I can measure this? Sure. That shift in thinking, that quiet defiance, changed everything. For the next 2,000 years, astronomers kept trying. They built better instruments. They made more careful observations. But the stars stayed stubbornly out of reach, too far, too faint, too still. Because here's the problem, stars don't move. Not in the way planets do. Planets drift across the sky. You can track them. You can measure their motion. But stars, they just sit there night after night in exactly the same place. Or so it seemed. And if they don't move, how do you measure how far away they are? The answer, it turns out, is parallax. Have you ever been in a car looking out the window and noticed how the trees close to you seem to fly by while the mountains far away barely move at all? That's parallax. It's the apparent shift in position of an object when you view it from different locations. Astronomers realized that if they could observe a star from two different points in Earth's orbit, say 6 months apart, the star should appear to shift slightly against the background of more distant stars. And if they could measure that shift, they could calculate the distance. It sounds simple. It's not. The problem is that stars are so far away, the shift is almost invisible. We're talking about fractions of a degree. Tiny, tiny angles that require telescopes of extraordinary precision and patience to detect. For hundreds of years, astronomers tried and failed. They'd think they found a shift, then realize it was just an error in their instruments, or a trick of the atmosphere, or wishful thinking. And then in 1838, a German astronomer named Friedrich Bessel finally did it. He chose a star called 61 Cygni, not because it was bright, it wasn't, but because it moved quickly across the sky, which suggested it might be relatively close. He observed it obsessively, night after night, month after month, and finally, after years of work, he detected the shift, the parallax. It was tiny, almost nothing, but it was real. And from that measurement, Bessel calculated that 61 Cygni was 10.4 light-years away. He was slightly off. Modern measurements put it at 11.4 light-years, but he was close enough. For the first time in human history, someone had measured the distance to a star, not the sun, not something in our solar system, but a star. A real distant, impossible star. Do you realize what that means? Bessel proved that the stars weren't just decorations. They were places, distant suns, entire worlds of their own. And the universe was suddenly devastatingly, unimaginably larger than anyone had guessed. But Bessel didn't call his measurement light years. That term came later. What he measured was in terms of astronomical units. AU. Remember that? The distance from the Earth to the Sun. 93 million miles. 61 Cygni, he found, was about 700,000 astronomical units away. 700,000 times the distance from the Earth to the Sun. A number so large it barely registers. It's like saying a star is very, very far. It tells you something, but it doesn't help you feel it. So astronomers needed a better unit, something that made sense, something that captured the sheer absurd scale of interstellar space. And that's when someone suggested, why not use light? Light is fast, the fastest thing in the universe. Nothing moves quicker, and light doesn't stop, doesn't slow down, doesn't get tired. It just goes, constantly, forever. So, if you measure distance by how far light travels in a year, you get something elegant, something that ties together speed and time and space in one neat package. 1 light year, the distance light travels in 365 days, 5.88 trillion miles, or if you prefer 9.46 trillion kilometers, or in astronomical units, 63,241 AU. Pick your number. They're all incomprehensible. But here's the beautiful part. Once you have light years, you can start building a map, a real map of everything. After Bessel, other astronomers started measuring more stars: Vega, Sirius, Alpha Centauri. One by one, the distances were calculated, and the universe opened up, not just in size, but in time. Because remember, distance and time are the same thing when you're measuring with light. Sirius, the brightest star in the night sky, is 8.6 light-years away. That means the light you see tonight left Sirius in 2016. When that light began its journey, David Bowie had just died. The Cubs had just won the World Series. You were younger. The world was different. And now, years later, that light finds you. Right here, right now. Isn't that strange? The present is always catching up to the past. And the past is always arriving in the present. The night sky is not a snapshot of now. It's a collage of then. Every star you see is a memory frozen in photons still traveling. Some of those memories are recent, some are ancient, and some are older than cities, older than civilizations, older than our species. But we'll get to that. Not yet. Right now, I want to stay with this moment, this shift in understanding. Because what Bessel and his colleagues did wasn't just mathematics, it was philosophy. They proved that we are not the center, that the universe is not small, that the stars are not ours. They belong to themselves, and they are so far away that the light we see tonight is already outdated by the time it arrives. Think about that for a second. Every observation we make of the cosmos is historical. We are not seeing the universe as it is. We are seeing the universe as it was, and the farther we look, the deeper into history we go. This is what light years really measure, not distance, history. Every star is a timestamp, every constellation is a timeline. And the night sky is a living archive of the past, written in light, stretched across a darkness we can barely fathom. But here's where it gets personal. Here's where the science becomes something softer. When Bessel measured 61 Cygni, he didn't just calculate a number. He changed the way we see ourselves. He made Earth smaller. He made the stars real. And he made the universe a place we could, in theory, visit. Not easily, not soon, but someday. Because once you know how far something is, you can start imagining the journey. You can start asking, could we go there? Could we build something fast enough? Could we reach another star before we grow old? And the answer for now is no, not even close. But the dream is there, the possibility. And that possibility was born the moment Bessel measured the parallax of a single faint star in the constellation Cygnus. He gave us a distance, and with that distance, he gave us hope. Of course, hope has a cost, because the distances Bessel and others measured were just the beginning. The nearby stars, the easy ones, the ones close enough that parallax still works. But what about the stars farther out? What about galaxies? What about the edge of the universe? Parallax doesn't work there. The angles are too small. The distance is too vast. The shifts too subtle even for our best instruments. So astronomers had to invent new rulers, new methods. Some involve brightness, some involve motion. Some involve the light itself, the way it stretches and shifts as the universe expands. But all of them, every single one, relied on that first measurement, that first light year, that first proof that the stars were not infinite, but finite. Far, yes, impossibly far. But not unreachable, not in theory, not if we could just figure out how to move fast enough. And so, the question changed. It was no longer, how far are the stars? It became, how do we get there? That question haunts us still. And it will continue to haunt us because the distances we've measured are not kind. They are not gentle. They are brutal. They are the kind of distances that break ships and lifetimes and species. But we keep measuring. We keep calculating. We keep looking up and asking, how far? Because maybe somewhere deep in the human mind, there's a belief that if we can name a distance, we can conquer it. If we can count the light years, we can cross them. Maybe we can't. Maybe we never will. Maybe the stars will remain what they've always been, distant lights beautiful and untouchable shining in the dark. But at least now we know how far they are. At least now we have a number. And maybe that's enough, to know the distance, to measure the impossible, to look at the stars and say, I see you, and I know how long your light has traveled to reach me. Perhaps that's all we were meant to do. Not to conquer the stars, but to witness them. To honor the light that crosses such terrible distances, just to meet our eyes for one fleeting second before it fades. And now that we know how to measure them, now that we have our light years and our parallax and our cosmic rulers, we can start asking harder questions. Questions that feel less like science and more like philosophy. Like, why can't we imagine these distances? Why do the numbers stop meaning anything once they get too large? What is it about the human brain that makes infinity feel the same as impossible? Let's find out. Here's something strange. You can imagine 100 apples. You can picture them, count them, even feel the weight of carrying them all at once. 1,000 apples, harder, but still possible. Your mind starts to see rows. Baskets may be a small warehouse, but 1,000,000 apples, a billion. Somewhere along the way, your brain stops picturing and starts guessing. The image dissolves. The number becomes just a word. A lot. Too many. More than I can hold. And that's the problem with light years. They live in that place where numbers stop meaning anything, where distance becomes abstract, where the mind quietly gives up. But why? Why can't we imagine them? What is it about the human brain that makes infinity feel the same as impossible? Let's find out. There's a term for this. Cognitive scientists call it number sense. It's one of the oldest parts of our brain, evolutionarily speaking. Ancient, hardwired. It helped our ancestors survive. When early humans looked at a tree full of fruit, they needed to know, is that enough to feed the group? When they saw a pack of predators, they needed to estimate, are there more of them or more of us? That ability, that quick mental math, kept us alive. And it works beautifully for small numbers. Studies show that most people can instantly recognize quantities up to about 4. Show someone 4 dots and they know it's 4 without counting. No effort, no thought. Just instant recognition. Researchers call this subitizing. It's fast, automatic, and accurate, but it only works for tiny numbers. Once you get past 4 or 5, the brain switches strategies. It starts estimating, grouping, guessing, and once you get past a few hundred, the brain starts to fail entirely. A psychologist named Stanislas Dehaene at the Collège de France has spent decades studying this. He found that when people are shown large numbers, say 1,000 versus 1/100, they can tell the difference. Barely. But the bigger the numbers get, the worse we become at distinguishing them. Show someone 10,000 and 11,000 and they'll struggle. Show them 100,000 and 110,000, and most people will just shrug. They know one is bigger, but they don't feel the difference. And that's the key word, feel. Because understanding numbers isn't just about logic, it's about intuition, about having a felt sense of magnitude. And our brains simply weren't built for magnitudes beyond our immediate experience. We evolved to count berries, not stars. To measure distances we could walk, not distances light travels in a year. To think in terms of days and seasons, not geological epochs or cosmic time scales. So, when someone says, a light year is 588 trillion miles, your brain does something interesting. It files that number under very big and moves on. It doesn't visualize it, doesn't internalize it. It just acknowledges the abstraction and lets it drift away. Let me show you how broken our intuition really is. Imagine I asked you how long is 1,000,000 seconds. Take a guess, just a rough estimate. Most people say something like a few days or maybe a week. It feels reasonable. 1,000,000 is big, but not that big, right? The answer is 11.5 days. Okay, fine, not too far off. Now, let me ask you this. How long is 1,000,000,000 seconds? A lot of people say a few months. Maybe a year if they were being generous. Because 1,000,000,000 is just 1,000 millions, right? So if 1,000,000 seconds is 11 days, then 1,000,000,000 seconds is, what, 11,000 days? That's about 30 years. Wait, 30 years. Yes, 1,000,000,000 seconds is 31.7 years. Did you feel that? That tiny lurch in your brain, that moment where the number suddenly becomes real. That's the problem. We hear billion and we think big million. But it's not. It's 1,000 million, and our brains can't hold the weight of that difference. Now, imagine trying to conceptualize a trillion, or 588 trillion, or the distances between galaxies measured in millions of light years, each light year already being an incomprehensible number on its own. It's no wonder we can't imagine it. We're not supposed to. Our brains weren't designed for this kind of thinking, and yet we try. We keep trying. Because there's something in us that refuses to let the universe stay abstract. We want to feel it. We want to hold it, even if we know we can't. So, scientists have come up with tricks, little tools to help us translate the cosmic scale into something human-sized, something we can almost touch. One of the most famous is called the cosmic calendar. Carl Sagan popularized it. The idea is simple. Take the entire history of the universe, all 13.8 billion years, and compress it into a single year. January 1st is the Big Bang. December 31st at midnight is right now. And everything that's ever happened, every star that's ever formed, every galaxy that's ever collided, fits somewhere in between. On this scale, the Milky Way forms in mid-March. Our solar system doesn't show up until early September. Dinosaurs appear on December 26th. They go extinct on December 30th. And all of recorded human history, every empire, every war, every invention happens in the last 10 seconds. before midnight on December 31st. 10 seconds. That's it. That's us. Does that help? Does it make the scale feel more real? Maybe. A little. But even this trick has limits, because compressing time into a calendar is still just a metaphor. It doesn't make you feel the weight of a billion years. It just gives you a new way to think about it. And thinking isn't the same as knowing. Here's another way to break your brain. Let's talk about speed. You're sitting still right now. Or at least you feel like you are, but you're not. You're moving fast, unbelievably fast. The Earth is spinning. Right now, as you listen to this, you're rotating at about 1,000 miles per hour. That's faster than the speed of sound. And you don't feel it, not even a little. The Earth is also orbiting the Sun at about 67,000 miles per hour. That's 18 miles every second. In the time it takes you to blink, you've traveled 50 miles through space. And you don't feel that either. But wait, it gets faster. The Sun is moving too. It's orbiting the center of the Milky Way at about 514,000 miles per hour. That's more than 500,000 miles per hour. And the Milky Way itself is moving pulled by gravity toward a cluster of galaxies called the Great Attractor at about 1.3 million miles per hour. Right now, as you sit here, you are hurtling through space at over 1 million miles per hour, and you feel nothing. Because everything around you is moving at the same speed. The air, the ground, the stars. It's all relative, all silent, all still. And that's the thing about cosmic scales. They don't feel real because they're too smooth, too constant, too far removed from anything we can sense directly. We're not built to feel the universe. We're built to feel the breeze, the warmth of sunlight, the texture of dirt under our feet. The universe is too big, too fast, too far for our senses to register. So we do what humans have always done. We build tools, telescopes, spectrometers, equations. We translate the incomprehensible into numbers, and then we translate the numbers into metaphors, and then we translate the metaphors into stories. And maybe that's okay. Maybe we're not supposed to understand the universe the way we understand a tree or a river. Maybe the universe is meant to stay a little mysterious, a little beyond us. But that doesn't stop us from trying. And it doesn't stop the feeling, that quiet vertigo, when you realize just how much we don't understand, how much we can't imagine. There's a concept in psychology called the illusion of explanatory depth. It's the idea that we think we understand things better than we actually do. Ask someone how a zipper works, and they'll say, "Oh, it's easy, the teeth interlock." But then ask them to draw it, to explain the mechanism in detail. And suddenly they realize they don't actually know. The same thing happens with cosmic distances. We throw around terms like light years and billions of miles as if they mean something, as if we've internalized them. But we haven't, not really. We've just learned the words, we've memorized the metaphors, and underneath the numbers are still incomprehensible, still abstract, still impossible. So, here's a question. Does it matter? Does it matter that we can't imagine these distances, that our brains fail when the numbers get too big? Maybe not. Maybe the point isn't to imagine it. Maybe the point is just to acknowledge it, to sit with the discomfort of not knowing, to let the universe be bigger than us. Because here's the truth, the universe doesn't care if we understand it. It's not waiting for us to catch up. It's not slowing down so we can keep pace. It just is, vast, indifferent, and utterly beyond us. And maybe there's something comforting in that, something freeing. We don't have to understand everything. We don't have to hold the whole universe in our heads. We can just witness it, let it wash over us. Let the numbers dissolve into awe, because awe doesn't require comprehension. Awe is what happens when comprehension fails, when the mind reaches its limit and says, "Okay, I give up. This is too much." And instead of fear, instead of frustration, there's just wonder. That's what light years give us. Not understanding, wonder. The kind of wonder that makes you feel small, yes, but also connected. part of something impossibly large, something that was here long before you and will be here long after you're gone. And isn't that enough to know that we exist inside something we can't fully imagine? To look up at the stars and think, I don't understand how far you are, but I see you, and you're beautiful. Maybe that's all we need, not to conquer the distance, not to shrink it down to something manageable, but to let it stay big, let it stay impossible, let it remind us gently that we are finite, and the universe is not. So, the next time you hear a number like 1 trillion miles or 1 billion light years, don't try to picture it. Don't try to hold it in your mind. Just let it be. Let it sit there too big to imagine, too vast to feel. And let that vastness be its own kind of answer. Because some things aren't meant to be understood. Some things are meant to be felt, softly, quietly, in the dark. And perhaps that failure to imagine isn't a failure at all. Perhaps it's the brain's way of protecting us, of letting us live in the present without being crushed by the infinite. But even so, there are moments when the distance becomes personal, when the numbers attach themselves to a single point of light, a single star, and suddenly the abstract becomes achingly impossibly real. There's a star out there, right now, as you listen to this. A small, dim, unremarkable star that most people have never heard of. It's called Proxima Centauri, and it's our closest neighbor, the nearest star to Earth that isn't the Sun. 4.24 light years away. That sounds close, doesn't it? Almost friendly, just 4 light years, a short hop across the cosmic street. If we could just build a fast enough ship we could visit, we could go there. We could see another sun with our own eyes. Except we can't. Not even close. Because 4.24 light years isn't close at all. It's so far, so devastatingly far, that every plan we've ever made to reach it has been nothing more than a dream wrapped in mathematics. Let me show you what close really means in space. Proxima Centauri is a red dwarf, a small star, cooler than the sun, dimmer. It doesn't shine bright enough to see with the naked eye, even though it's the closest one we have. Scientists discovered it in 1915. A Scottish astronomer named Robert Innes was studying photographic plates at the Union Observatory in South Africa when he noticed something odd, a faint star that seemed to move slightly against the background of more distant stars. That movement meant it was close, relatively speaking, and when he calculated the distance, he found it was closer than Alpha Centauri, the bright star everyone thought was our nearest neighbor. Proxima Centauri. The name means nearest. And for over a century, it's held that title, the closest star, the one that in theory we could reach first. But here's the problem. Here's the truth that no one likes to talk about. 4.24 light years is 25 trillion miles. Let that sit for a moment. Not 25 million, not 25 billion, 25 trillion. That's 25 with 12 zeros after it. A number so large it doesn't fit comfortably in the mind. Now, let's talk about speed, because if we're going to visit Proxima Centauri, we need to move fast. The fastest human-made object ever built is the Parker Solar Probe. NASA launched it in 2018 to study the sun, and it's currently screaming through space at about 430,000 miles per hour. 430,000 miles per hour. That's fast. Faster than anything we've ever created. Faster than you can imagine. In 1 hour, it travels farther than the distance from New York to Tokyo. Twice. So how long would it take the Parker Solar Probe to reach Proxima Centauri? 633 years. 6,633 years. That's how long it would take our fastest spacecraft to reach the nearest star. When it launched, the Bronze Age was ending. When it arrived, we'd be living in a world we can't even begin to predict. Civilizations would rise and fall. Languages would be born and forgotten. The people who built the probe would be dust. Their children's children's children, 100 generations deep, would be dust. And the probe would still be flying. Alone, silent, crossing a darkness so complete, so empty that it might as well be traveling through nothing at all. That's what 4.24 light years means. That's what close looks like in space. But maybe you're thinking, okay, fine, the Parker Solar Probe is fast, but it wasn't designed to go to other stars. What if we built something specifically for interstellar travel? What if we pushed the limits of engineering and physics? How fast could we really go? Let's say we built a ship that could travel at 10% the speed of light. That's wildly optimistic, insanely ambitious. But let's say we did it. 10% of light speed. That's about 67 million miles per hour. At that speed, you could circle the Earth in 20 seconds. You could reach the moon in 3.5 seconds. It would feel almost like magic. How long to Proxima Centauri? 42 years. 42 years. That's an entire human lifetime. You'd leave as a young adult and arrive as an old one, if you arrived at all. And that's assuming the ship doesn't break, doesn't collide with anything, doesn't run out of fuel or power or hope somewhere in the middle of the void. And remember, this is the closest star, the easy one, the one right next door. Now, here's the part that breaks people's hearts. Proxima Centauri isn't alone. It's part of a triple star system. The other two stars, Alpha Centauri A and B, orbit each other. Proxima orbits them both distantly, like a shy cousin lingering at the edge of a family reunion. In 2016, scientists discovered something extraordinary, a planet orbiting Proxima Centauri. They called it Proxima B, and it's in the habitable zone, the Goldilocks zone. Not too hot, not too cold. The region where liquid water could in theory exist on the surface. For a brief shining moment, people got excited. A potentially habitable planet, right next door. Maybe we'd found a new Earth, a place we could go, a backup, a second chance. But the excitement didn't last long, because the more we learned about Proxima B, the less hospitable it seemed. Proxima Centauri is a red dwarf. And red dwarfs are violent. They flare constantly. Massive bursts of radiation that blast out into space, scorching anything nearby. Proxima B is close to its star, very close. It orbits once every 11 days. That means it's tidally locked. One side always faces the star. One side is always in darkness, like the moon facing Earth, but worse, far worse. The side facing the star is blasted by radiation. The side facing away is frozen in eternal night. And in between, in the thin twilight zone, where temperatures might be bearable, the winds are unimaginable. Howling storms driven by the temperature difference between eternal day and eternal night. And even if the planet had an atmosphere once which it might have the radiation from Proxima Centauri's flares likely stripped it away. Layer by layer, molecule by molecule, until nothing was left but bare rock and silence. So, Proxima B isn't a second Earth. It's a reminder, a lesson in just how rare and fragile life might be, how specific the conditions need to be, how lucky we are to live on a world that doesn't kill us just by existing. But here's the strange part. Even knowing all of that, even knowing Proxima B is probably a dead, irradiated wasteland, we still dream about going there. We still run the calculations, design the ships, write the proposals, because it's close, because it's the nearest thing we have to a destination. Because humans have always been the kind of species that looks at an impossible distance and says, what if? Let me give you another way to picture this. Another way to feel just how far Proxima Centauri really is. Imagine the sun is the size of a basketball, just a regular basketball sitting in your driveway. On that scale, the Earth would be a tiny grain of sand about 26 feet away. Pluto would be another grain of sand about 1,000 feet away. The edge of our solar system, the heliopause where the sun's influence finally fades, would be about half a mile out. Now, where would Proxima Centauri be on this scale, 4,000 miles away? If the sun is a basketball in your driveway, Proxima Centauri is another basketball sitting somewhere near the opposite coast of the United States. New York to Los Angeles. That's the distance. That's the gap we're trying to cross. And in between, nothing. Empty space, no planets, no asteroids, no comets, just darkness. A void so complete that if you started walking, you'd die of old age 1,000 times over before you made it halfway. That's the scale of interstellar space. That's what we're up against. And yet, we keep trying. In 2016, a project called Breakthrough Starshot was announced. The idea is audacious. Beautiful, really. They want to send tiny spacecraft, each one no bigger than a postage stamp, to Proxima Centauri. How? With lasers. Enormous ground-based lasers that would push light sails attached to the tiny probes, accelerating them to 20% the speed of light. At that speed, the probes could reach Proxima Centauri in about 20 years. Not a lifetime. Not 6,000 years, just 20. Fast enough that the people who launched them might still be alive to receive the data when it comes back. It's a brilliant plan, elegant, hopeful, and it might even work someday. If we can solve the engineering problems, if we can build lasers powerful enough, if we can keep the probes on course, if the radiation doesn't fry their circuits, But even if it works, even if we send those tiny probes screaming across the void at 1/5 of the speed of light, they won't carry people. They won't carry life. They'll just be cameras, messengers, little mechanical eyes sent to look at a place we'll never touch. And maybe that's enough. Maybe that's all we were ever meant to do. Not to conquer the stars, but to witness them. To send our curiosity ahead of us, even if our bodies can never follow. There's something humbling in that. Something that puts us in our place. We are not the center of the universe. We are not destined to spread across the galaxy like some science fiction dream. We are small, fragile, tied to this one pale blue dot in a vast and different cosmos. But we still reach. We still dream. We still look at Proxima Centauri, 25 trillion miles away, and think, maybe someday. And maybe that's enough, to know the distance, to feel the weight of it, to understand just how far close really is, and to keep dreaming anyway. Because that's what humans do. We measure the impossible. We calculate the absurd. We look at distances that should crush hope, and we build ships anyway. Not because we think we'll succeed, but because we can't help ourselves. We are a species that dreams of stars, even when the stars are too far to reach. Even when the math says no. Even when the universe itself seems designed to keep us here, on this one small world, under this one small sun. We dream anyway. Proxima Centauri will never feel close. Not in our lifetimes. Maybe not ever. But it's there, shining faintly in the southern sky. A reminder that the universe is full of places we'll never go. Full of suns we'll never feel. Full of distances we'll never cross. And somehow, that makes it more beautiful, not less. Because the stars don't need us to reach them. They're fine on their own, burning quietly in the dark, waiting for no one, expecting nothing. And we down here on our little world can look up and know there's a star out there, our closest neighbor, 4.24 light years away. And even though we can't touch it, even though we'll probably never reach it, we know it's there. And that knowing, that quiet acknowledgement of distance, is its own kind of connection. A thread stretched across the void, too thin to see, too fragile to hold, but there nonetheless. And while Proxima Centauri sits there, locked in its slow orbit, occasionally flaring with violent light, there are other travelers in the darkness. Objects that have no star to call home, no orbit to follow, just endless drifting through the space between. And in their loneliness, we begin to understand what emptiness really means. On October 19th, 2017, a telescope in Hawaii saw something it had never seen before. A small object, dark, moving fast, too fast. It was already past the sun, already leaving our solar system, and no one had noticed it arriving. At first, astronomers thought it was a comet, then maybe an asteroid. But the more they looked, the stranger it became. It wasn't orbiting anything. It wasn't bound to the sun. It was just passing through, a visitor from somewhere else, from the space between stars. They named it Oumuamua, a Hawaiian word meaning scout or messenger, the first of its kind, the first interstellar object ever detected passing through our solar system. And by the time we realized what it was already gone. In the vastness between stars, most things drift alone. Oumuamua reminds us that space isn't filled with light and planets and bustling solar systems. Space is filled with silence, with emptiness, with travelers who have no home. Let me tell you what loneliness really looks like. Oumuamua is small, maybe 300 feet long, shaped like a cigar or possibly a pancake. Scientists still aren't sure. It tumbled as it moved, spinning end over end every 7.3 hours, catching sunlight, and then losing it again in a slow, wobbling rotation. When it passed closest to the sun, it was moving at about 196,000 miles per hour. Fast. Faster than anything naturally orbiting our sun. And it had to be fast because it didn't belong here. It was just passing through. A cosmic hitchhiker briefly illuminated by our star before vanishing back into the dark. But here's what makes Oumuamua extraordinary. Here's what keeps astronomers awake at night. It came from somewhere far away, and it's been traveling for a very, very long time. Scientists traced its trajectory backward, trying to figure out where it came from. The best guess, somewhere in the direction of the star Vega. But Vega is 25 light years away. And Oumuamua isn't fast enough to have come from there recently, not even close. If it did come from Vega's neighborhood, it would have taken about 300,000 years to reach us. 300,000 years, drifting, alone, in the cold, in the dark, in a space so empty that most of the time, it wasn't even near a star. Think about that. For 300,000 years, this object tumbled through the void. No light, no warmth, no planets, just darkness and distance and the faint pull of gravity from objects too far away to matter. It passed nothing, saw nothing, felt nothing, just drifted silent and dark through a universe that didn't notice it was there. And then for 11 days in October 2017, it passed through our solar system. A tiny blip of sunlight and observation, a brief moment of being seen. And then it was gone again. Back into the darkness, back into the space between. It will drift for another few 100,000 years before it gets close to another star. Maybe longer, maybe forever. That's what interstellar space is. Not a highway, not a road, not even a path. Just emptiness, unimaginable emptiness. And objects like Oumuamua drifting through it, carrying no message, no purpose, no story. Just inertia. Just motion left over from some ancient event we'll never know about. But let's talk about that emptiness, because I don't think most people understand just how empty space really is. When we look up at the night sky, we see stars. Lots of them. The sky feels full, crowded almost. Like the universe is packed with light. But that's an illusion, a trick of perspective. The stars we see are just the bright ones, the nearby ones. And even they are separated by distances so vast that if you tried to visit them all, you'd spend almost all your time traveling through nothing. Here's a number that might help, or might make it worse. In interstellar space, the average density is about 1 atom per cubic centimeter. 1 atom. In a space the size of a sugar cube, that's not just empty, that's almost perfectly empty. It's closer to a vacuum than anything we can create in a laboratory on Earth. For comparison, the air you're breathing right now contains about 10 quintillion molecules per cubic centimeter. That's 10 with 18 zeros after it. The difference between the air around you and interstellar space is incomprehensible. If you were floating out there in the space between stars, you could stretch out your arms and spin in a circle, and the chances of touching even a single atom would be almost zero. And Oumuamua. It traveled through that emptiness for hundreds of thousands of years, alone, untouched, unnoticed. But here's where it gets stranger. Because Oumuamua isn't unique, it's just the first one we saw. Scientists estimate that at any given moment, there are thousands of interstellar objects passing through our solar system. Maybe tens of thousands. We just don't see them. They're too small, too dark, too fast. They slip through unnoticed like shadows in the night. Most of them are probably chunks of ice or rock, debris ejected from other solar systems during planetary formation, or fragments knocked loose by gravitational interactions, or orphans cast out into the dark by the chaotic violence of their birth. Some of them have been traveling for millions of years, some for billions. Older than our sun, older than Earth, older than anything we can touch. And they drift, endlessly, silently, through a darkness so complete, so total, that the word empty doesn't even begin to describe it. Have you ever been somewhere so quiet you could hear your own heartbeat, where the silence felt heavy, almost physical, pressing against your ears? That's nothing compared to interstellar space. In space, there's no air to carry sound, no medium for vibrations to travel through. Even if you screamed, even if you exploded, no one would hear it. Not because it's too far away, but because sound simply doesn't exist there. It's not quiet, it's silent, perfectly, absolutely silent. The kind of silence that would drive a human mind to madness if it lasted too long. And Oumuamua has been drifting through that silence for longer than our species has existed. When Oumuamua began its journey, humans hadn't invented writing yet, hadn't built cities, hadn't even figured out agriculture. We were still hunter-gatherers, scattered in small tribes, trying to survive. And this object, this small, dark, tumbling rock, was already out there, already drifting, already alone. It makes you wonder, doesn't it? What else is out there? What other objects are traveling through the dark, unseen, unnoticed, carrying no memory of where they came from or where they're going? But here's the part that haunts me, the part I can't stop thinking about. When astronomers first detected Oumuamua, they noticed something odd. As it moved away from the sun, it accelerated, slightly, just a tiny bit, but enough to measure. At first they thought it might be a comet. Comets accelerate as they heat up, releasing gas and ice that acts like a tiny rocket engine. But Oumuamua didn't have a tail, didn't show any signs of outgassing. It was just accelerating, for no obvious reason. Some scientists suggested it might be a solar sail, a thin, flat object pushed by sunlight, or maybe even an alien spacecraft, though most researchers dismiss that idea as unlikely. The truth is, we don't know. We probably never will, because by the time we realized Oumuamua was strange, it was already too far away to study closely. It's gone now, out past Neptune, out past the Kuiper Belt, headed back into the darkness it came from. And we're left with questions, with mysteries, with the uncomfortable realization that the universe is full of things we don't understand. Things that pass through our little corner of space and vanish before we can figure out what they are. Oumuamua was a gift, a rare glimpse into the space between stars, a reminder that the universe is far stranger, far lonelier, far emptier than we usually imagine. But it's also a reminder of something else, something quieter, something almost philosophical. Everything in the universe is in motion, everything is drifting. Planets orbit stars, stars orbit galaxies. Galaxies drift through the expanding fabric of space. Nothing stays still. Nothing is permanent. And in between all of that motion, in the vast dark spaces where nothing lives and nothing shines, there are travelers, silent, forgotten, alone, carrying no message, no meaning, just inertia. Oumuamua is one of them. And so, in a way, are we. We're all just travelers drifting through space on a rock that orbits a star, that orbits a galaxy, that's moving through a universe we barely understand. The difference is we have light, we have warmth, we have each other. Oumuamua has none of that. Just the cold, just the dark, just the endless patient drift. And maybe that's okay. Maybe not everything in the universe needs to be warm or bright or alive. Maybe some things are just meant to drift, to exist without purpose, to travel without destination. There's a kind of peace in that, isn't there? A kind of freedom. No expectations, no obligations, just motion, just time, just the slow, inevitable journey through the dark. But for us here on Earth, in our tiny bubble of warmth and air and life, Oumuamua is a reminder, a whisper from the void, a message that says, the universe is bigger than you think, emptier than you imagine, and full of things you'll never see, never touch, never understand. And that's okay. We don't need to understand everything. We don't need to catch every traveler that passes through. We just need to look up, to notice, to acknowledge that we are not alone in being alone. Somewhere out there right now, Oumuamua is still drifting, still tumbling, still moving away from the sun at 60,000 miles per hour. It won't be back. It won't visit another star system for hundreds of thousands of years, maybe millions, maybe never. It's just going, endlessly, silently, through a space so vast, so empty that even the word space feels inadequate. And in that emptiness, in that terrible, beautiful silence, there's a truth we don't often talk about, a truth that feels too heavy to hold for very long. The universe doesn't care. It doesn't notice. It doesn't watch. It just is, vast and indifferent and utterly achingly empty. And we here on our little world are the ones who care, who notice, who watch, who try to make sense of the emptiness by filling it with stories and names and meaning. Oumuamua didn't ask to be named, didn't ask to be seen. It was just passing through. But we saw it, and we named it. And for a brief moment, we made it matter. Maybe that's all we can do. Maybe that's all we were ever meant to do. Not to conquer the darkness, not to fill the emptiness, but to witness it, to name it, to let it pass through quietly, and remember that it was here, even if it's already gone. And while Oumuamua continues its silent journey into the incomprehensible emptiness between stars, we drift too, but not alone. We drift inside something vast and spinning a structure so large that light itself takes millennia to cross it. And within that structure, we are but dust suspended in a river of stars that flows in ways we're only beginning to understand. You are right now inside something so vast that light takes 100,000 years to cross it. You can't see it. Not all of it. Not from where you are, but it's there, spinning, slowly, silently. A river of stars so large that our entire solar system is just a speck of dust caught in its current. We call it the Milky Way, our galaxy, our home. And most of us will live our entire lives without ever really understanding where we are inside it. Let me show you. Right now, the Earth is orbiting the Sun. The Sun is orbiting the center of the Milky Way. And the Milky Way itself is drifting through space pulled by invisible forces we're only beginning to map. We are not still. We are not floating. We are falling, constantly, through a structure so immense that even the distances we've talked about so far, the light years to nearby stars, become almost meaningless. Because the Milky Way is home to somewhere between 100 billion and 400 billion stars. And we are just one of them. One small, ordinary star tucked away in a quiet corner, far from the chaos at the center. But how far? And what does far even mean when you're talking about a galaxy? Let's start with a number, a distance, a measurement that should by now feel familiar. The Sun is located about 26,000 light years from the center of the Milky Way. 26,000 light years. Not 26, not 260. 26,000. That's the distance between us and the heart of our galaxy, the place where everything in a sense begins. Now remember what a light year means. It's not just distance, it's time. When you look toward the center of the Milky Way, when you point a telescope in that direction and capture the light, you're not seeing it as it is now. You're seeing it as it was 26,000 years ago. 26,000 years ago, humans were still living in the Stone Age. We hadn't invented writing, hadn't built cities, hadn't even figured out agriculture yet. We were nomads following herds, painting on cave walls, trying to survive. And the light that left the galactic center back then, the light from those ancient stars, is only just now reaching us. Tonight. This moment. As you listen to these words, that light has been traveling alone through the darkness for longer than recorded history, longer than empires, longer than language itself, and it's still arriving, still reaching us. A constant stream of ancient photons carrying news from a place we'll never visit. But here's the strange part, the beautiful part, really. We're not just observers, we're participants. We're moving too. The sun and everything orbiting at Earth included is flying through space at about 514,000 miles per hour, 500,000 miles per hour. That's how fast we're moving right now. As you sit here, as you breathe, as you listen, you are traveling through the galaxy at a speed that would take you from New York to Los Angeles in about 30 seconds. And you don't feel a thing, because everything around you is moving at the same speed. The air, the ground, the moon, the planets, the stars. It's all moving together, locked in the same orbital dance, spinning around the galactic center like a carousel that never stops. But even at that speed, even traveling 500,000 miles per hour, it takes us 230 million years to complete one full orbit around the galaxy. 230 million years. That's called a galactic year. And in Earth's entire history, we've only completed about 20 of them. When the sun was in this same position last time, dinosaurs were just beginning to evolve. The supercontinent Pangaea was still intact. There were no birds, no flowers, no mammals larger than a mouse. And now, here we are again. One orbit later. The galaxy hasn't noticed. It just keeps spinning. Patient. Relentless. Indifferent to the small lives playing out on its edges. So, where are we exactly? What does our neighborhood look like? The Milky Way is a spiral galaxy. It has arms. Long curving structures made of stars and gas and dust, spiraling outward from the center like water swirling down a drain. We live in one of those arms. It's called the Orion Arm, or sometimes the Orion Spur, a smaller, less prominent arm tucked between two larger ones. We're not in the main spiral, not in the thick of things. We're in a quiet spot, a backwater. A place where stars are spread out, where the density is low, where not much happens. And maybe that's a good thing. Maybe that's why we're here at all. Because closer to the center, things get chaotic, violent. Stars are packed together so tightly that gravitational interactions are common. Collisions, supernovae, black holes, life fragile and slow as it is probably couldn't survive there. Too much radiation. Too much chaos, too much disruption. But out here on the edge in the quiet, there's stability. There's time. Time for planets to form. Time for water to pool. Time for chemistry to become biology. Time for life to take root and grow and look up at the stars and wonder where it is. And where we are, it turns out, is in a relatively safe bubble, a region of space where the local density of stars is low, where supernovae are rare, where the sun can orbit peacefully for billions of years without being disturbed. Scientists call this the local bubble. It's a region about 1,000 light-years across, carved out by ancient supernova explosions that cleared away most of the gas and dust. We're inside it, protected in a way, shielded from the worst of the galaxy's violence. But even so, we're not isolated. The Milky Way is full of structure, full of currents, streams of stars flowing through the dark, clusters held together by gravity, nebulae where new stars are being born, and at the center something massive, something dark, at the very heart of the Milky Way. 26,000 light-years away, there is a black hole, not a small one. Not a stellar mass black hole formed from a single collapsing star. This one is supermassive, a monster. It has a name, Sagittarius A, and it contains the mass of about 4 million suns compressed into a region smaller than the orbit of Mercury. 4 million suns. All of that mass, all of that gravity, packed into a space you could cross in a few minutes if you were traveling at the speed of light. And it's pulling, constantly, relentlessly. Everything near the galactic center orbits it. Stars whip around it at incredible speeds, some completing an orbit in just a few years. We've watched them, tracked them, measured their motion, and from those measurements, we've confirmed there's something there, something invisible, something so dense that not even light can escape it. But here's the thing. Sagittarius A is far away, 26,000 light years. And at that distance, its gravity is almost irrelevant to us. It doesn't pull on the sun, doesn't affect Earth, doesn't change our orbit in any measurable way. We're too far, too distant, too small to matter. And maybe that's comforting, maybe it's unsettling, to know that at the heart of our galaxy, there's a black hole millions of times more massive than our sun, and it doesn't even notice us. We're so far out on the edge, so insignificant that we might as well not exist. But we do exist, and we're here, orbiting, drifting, slowly making our way around the galaxy 1 year at a time, one orbit every 230 million years. It makes you think, doesn't it? About scale, about position, about what it means to be here, when here is such a small, quiet, forgettable place. Most people, when they think about the Milky Way, picture something distant, something you see in photographs, a band of light across the sky, beautiful, remote, separate from us. But that's not what the Milky Way is. The Milky Way isn't something you look at. It's something you're inside. You're part of it. You're made of it. Every atom in your body was forged in a star that lived and died somewhere in this galaxy. You are quite literally made of stardust. Galactic dust, recycled matter from ancient stars that exploded billions of years ago. And now here you are, a temporary arrangement of atoms orbiting a star inside a galaxy, wondering what it all means. Does it mean anything I don't know? Maybe not. Maybe the galaxy doesn't care about meaning. Maybe it just spins, forever, patiently, waiting for nothing. But we care, we notice. We try to understand. And in that trying and that reaching, there's something almost defiant. Something that says, I am small, yes. I am temporary, yes. But I am here, and I am paying attention. And maybe that's enough. To notice where you are. To understand even just a little the structure you're part of. The motion you're caught in. The slow, patient spin of a galaxy that will outlive you by trillions of years. Because here's the truth, you will never see the Milky Way the way it actually is. Not from here, not from inside. You can look up at the sky and see a slice of it, a thin band of stars stretching overhead. But you'll never see the spiral, never see the arms, never see the full structure. To see that you'd have to leave. You'd have to travel tens of thousands of light years away, far enough to turn around and look back. And by the time you got there, if you ever could, the galaxy would have moved, changed, evolved. The stars you left behind would be in different positions. The spiral arms would have rotated. The galaxy you'd see wouldn't be the one you left. Because the Milky Way is not static. It's not frozen. It's alive in a sense, constantly changing. Stars are born, stars die. Gas clouds collapse. Nebulae glow. Black holes feed, and the whole thing spins slowly, majestically, utterly indifferent to the tiny lives happening inside it. And we here on Earth are just passengers, riding the current, spinning with the rest, watching the stars drift by and always wondering where we are and where we're going. But here's something most people don't know, something that changes how you think about the Milky Way. We're not alone. I don't mean aliens, I mean galaxies. The Milky Way is not the only galaxy. It's not even the biggest galaxy nearby. And it's not sitting still. Right now, as you listen to this, the Milky Way is drifting through space, moving. being pulled by the gravity of other galaxies, galaxies we can see faintly in the night sky. The closest large galaxy to us is Andromeda. It's about 2.5 million light-years away, and it's coming toward us. Not slowly, not carefully, it's coming fast, at about 68 miles per second. In galactic terms, that's a collision course. In about 4.5 billion years, Andromeda and the Milky Way will collide. They'll merge. They'll become one massive galaxy, chaotic and bright and utterly transformed. But don't worry. When I say collide, I don't mean stars will smash into each other. Stars are too far apart for that. Even when two galaxies merge, the stars mostly just pass by each other, like ghosts slipping through walls. But the shape will change, the structure will break, the spiral arms will dissolve, and the galaxy we call home will become something new, something we'd barely recognize. But we won't be here to see it. Not us, not our sun. In 4.5 billion years, the sun will be dying, swelling into a red giant, consuming the inner planets. Earth will be long gone, lifeless, burned, a memory. And the Milky Way, the galaxy that held us for so long, will be unrecognizable, twisted, merged, transformed into something new. It's strange, isn't it? To think that the galaxy itself has a lifespan, that even this vast ancient structure is temporary, that nothing, not even a river of stars, lasts forever. But for now, the Milky Way is here, spinning, patient, quiet, and we're inside it, living our brief, bright lives, orbiting a small star in a quiet arm far from the center, far from the chaos. And maybe that's all we need to know, that we're here, that we're part of something larger, that we're spinning through the dark at 500,000 miles per hour, carried by forces we barely understand, toward a future we'll never see. But the stars will still be here. The galaxy will still spin. And the light, ancient and patient, will keep traveling, crossing the void, finding eyes that wonder, finding minds that ask, where are we and how far is far? But even as we orbit, even as we drift through this island of stars, something else is moving toward us. Something vast and distant, crawling across the darkness at speeds we can measure but barely comprehend. And when it arrives, when these two rivers of stars finally meet the sky, itself will be rewritten. There's something in the sky, moving, slowly, silently, coming closer. You can see it on a clear night if you know where to look. A faint smudge of light, soft, ghostly, easy to miss if you're not paying attention. It's called Andromeda, and it's falling toward us. Not someday, not maybe. Right now, this moment, as you breathe, as you listen. Andromeda is hurtling through space at 68 miles per second, closing the distance between us and it, and in about 4.5 billion years, it will arrive. And when it does, the sky will be rewritten, the stars will rearrange, and everything we call the Milky Way will become something new. This is the story of a collision that's already begun, a slow-motion crash between two rivers of stars, a merger that will take millions of years to complete. And we are here now watching it unfold in the only way we can, by looking at light that's already 2.5 million years old. Let me tell you what it means to fall through space for that long. Andromeda is a galaxy, not a small one. It's bigger than the Milky Way, more massive, more stars. Maybe 1 trillion of them all spinning together in a great spiral, bound by gravity, drifting through the darkness. And it's 2.5 million light years away. That means the light you see when you look at Andromeda tonight left that galaxy 2.5 million years ago. When that light began, its journey, humans didn't exist yet. Not modern humans anyway. Our ancestors were still small-brained, tree-dwelling primates just beginning to walk upright. And the light traveled, alone, crossing the void, one photon at a time, for 2.5 million years, through the emptiness between galaxies, through the cold, through the dark, until tonight, until now, until it reached your eye, You are looking at the past, not a recording of it, the actual past, still arriving. But here's the strange part, the beautiful, unsettling part. Andromeda isn't where you see it, not anymore. It's closer, much closer, because light takes time to travel, and in the 2.5 million years it took for that light to reach us, Andromeda has been moving, coming toward us, pulled by gravity, by the invisible thread that connects all massive things in the universe. Right now, in this moment, Andromeda is about 2.5 million light years away, but it's moving at 68 miles per second. That's about 244,000 miles per hour. Fast, not compared to light, but fast enough. At that speed, Andromeda closes the distance between us by about 1.5 billion miles every year. That sounds like a lot. It is a lot. But the gap is so vast, so incomprehensibly large, that even at that speed, it will take billions of years for Andromeda to arrive. 4.5 billion years. That's the estimate. That's how long we have before the collision begins. But here's the thing most people get wrong. When scientists say collision, they don't mean what you think they mean. Stars won't smash into each other. Planets won't explode. The sun won't be destroyed. Because the distances between stars, even within a galaxy, are so vast that when two galaxies merge, most of the stars just pass by each other, like two clouds of smoke drifting through one another, interpenetrating, mixing, but not colliding. The space between stars is so large that even when 1 trillion stars from Andromeda pass through the Milky Way, the chances of any two stars actually hitting each other are almost zero. Almost, not quite. Some stars will get close enough for gravity to pull them off course, close enough to be flung out into the void, orphaned cast into the darkness between galaxies where they'll drift alone for the rest of time. But most stars will survive. They'll just end up in different places, different orbits, different neighborhoods. The galaxy will be scrambled, rearranged, transformed. And the shape, the beautiful spiral structure we call the Milky Way will dissolve. The arms will break, the disk will warp, and over millions of years, the two galaxies will merge into a single massive elliptical galaxy, a blob of stars, chaotic, dense, bright. Astronomers have already given it a name. They call it Milkomeda, a blend of Milky Way and Andromeda, the galaxy that will exist when we are long gone, when the sun is a cooling ember, when Earth is a memory. But let's not get ahead of ourselves. Let's stay here. Let's talk about what's happening now, because the collision has already begun, not the physical collision, the gravitational one. Andromeda and the Milky Way are already pulling on each other. The gravity between them, weak as it is over such vast distances, is real, measurable, and it's been pulling for billions of years. In fact, some scientists suggest that Andromeda and the Milky Way have been circling each other for a very long time, orbiting, slowly, like two dancers moving closer with every turn, until eventually, inevitably, they embrace. This isn't the first time galaxies have collided. It's not even rare. The universe is full of galaxy mergers. We see them everywhere, through telescopes, frozen in time by the slowness of light, galaxies tangled together, spirals being torn apart, gas clouds igniting with new stars, black holes spiraling inward. It's violent, beautiful, destructive, and creative at the same time. Because when galaxies collide, even though stars don't hit each other, the gas clouds do. And when gas clouds collide, they heat up, compress, ignite. New stars are born. Thousands of them, maybe millions. The collision between Andromeda and the Milky Way will trigger a burst of star formation, unlike anything our galaxy has seen in billions of years. The sky will light up, not all at once, not in a way humans could ever witness, but over millions of years, the rate of star birth will skyrocket, and somewhere in that chaos in those new stars, maybe new planets will form, new worlds, new chances for life. But we won't be here to see it. Not us, not Earth, not even the sun. Because here's the uncomfortable truth. The collision between Andromeda and the Milky Way will happen in 4.5 billion years, but the Sun will start dying in about 5 billion years, maybe a bit less. The two timelines are close, uncomfortably close, and depending on how things unfold, depending on the exact timing and trajectories, the Sun might still be around when the galaxies begin to merge. It might witness the first stages, the first gravitational distortions, the first burst of new stars. But by the time the merger is complete, by the time Milkomeda fully forms, the Sun will be gone, swollen into a red giant, its outer layers blown into space, its core collapsing into a white dwarf, a dying ember cooling slowly in the dark. And Earth will be gone long before that. In about 1 billion years, maybe less, the Sun will grow hot enough that the oceans will boil. The atmosphere will strip away. Life, if it still exists, will die. And the planet will become a barren, scorched rock orbiting a dying star. So no, we won't see the collision. We won't witness Milkomeda. We won't know what the new galaxy looks like, or how it spins, or where our Sun ends up in the final configuration. But someone might, something might. If life survives, if it finds a way to leave Earth, to spread, to adapt, to endure, then maybe billions of years from now, some distant descendant of ours will look up at the sky and see Andromeda not as a faint smudge, but as a blazing arc of stars stretching across the heavens. And they'll know what we knew, that it's falling, that it's been falling for a very long time, and that the collision, slow and patient and inevitable, has finally arrived. But let's talk about what we can see now. Because even though Andromeda is still 2.5 million light years away, we can already observe the effects of its approach. The Milky Way is not perfectly still. It wobbles slightly. The disk isn't flat. It's warped, bent, like a record that's been left in the sun too long. And part of that warping, scientists believe, is due to Andromeda's gravity, a distant tug, a reminder that we're not alone, that we're part of something larger. The local group, that's what astronomers call it. The cluster of galaxies that includes the Milky Way, Andromeda, and about 50 smaller galaxies, all of them bound together by gravity, all of them orbiting a common center of mass, all of them in a sense falling toward each other. Andromeda and the Milky Way are the two largest members of the local group, the dominant ones, and their gravity shapes everything else. Smaller galaxies orbit them. Some get too close and are torn apart, consumed, absorbed into the larger structures. It's a kind of cosmic cannibalism, galaxies eating galaxies, growing larger, more massive, more complex, until eventually they merge, and the process starts over. This has been happening for billions of years. The Milky Way itself is a product of mergers. Our galaxy has consumed dozens of smaller galaxies over its lifetime. We can still see the remnants, streams of stars, ghostly trails in the sky, evidence of galaxies that once existed now scattered and dissolved into the Milky Way's structure. And Andromeda is the same. It's eaten galaxies too, grown fat on the matter of smaller neighbors. And now it's coming for us. Not with malice, not with intent, just with gravity. The oldest, slowest, most patient force in the universe. There's something poetic about that, isn't there? Two galaxies, two rivers of stars, both products of ancient violence, both shaped by billions of years of collisions and mergers and chaos. And now they're about to become one. Not because they chose to, not because of anything they did, just because gravity pulls, always, inevitably, until everything that can fall together does. And maybe that's the lesson, the quiet, uncomfortable lesson that the universe keeps teaching us. Nothing lasts, not stars, not galaxies, not even the vast structures we think of as permanent. Everything is in motion, everything is falling, and eventually everything merges, everything dissolves into something new. But here's the strange comfort in that, the thing that makes it bearable. When Andromeda and the Milky Way merge, nothing will be lost. Not really. The stars will still exist. The matter will still be there. It will just be rearranged, reformed, reshaped into something new. And maybe that new galaxy, that future Milkomeda, will be more beautiful than what came before. Maybe it will be brighter, more alive, full of new stars and new worlds and new chances for something remarkable to happen. Or maybe it won't. Maybe it will just be another elliptical galaxy, another blob of stars, ordinary, unremarkable, indistinguishable from billions of others scattered across the universe. We'll never know. We can't know. The future is too far away, too uncertain, too dependent on things we can't predict. But we can look up. We can see Andromeda. We can measure its motion, calculate its trajectory, and know with certainty that it's coming. And maybe that's enough. To witness the beginning of something that will take billions of years to complete. To see the first act of a story that will end long after we're gone. Because that's what light years give us. Not just distance, not just time, but perspective. A sense of scale, a reminder that we are part of something so much larger, so much older, so much more patient than we can ever be. Andromeda is falling, has been falling for billions of years, will keep falling for billions more. And we here now, in this brief moment of awareness, get to watch, to measure, to understand just a little what it means to be caught in the slow, inevitable dance of galaxies. And while Andromeda drifts closer year by year, photon by photon, carrying the light of 1 trillion stars across an ocean of emptiness, there's something even farther out there, something so distant that the light we see left its source when the universe itself was young, when galaxies were just beginning to form, when time and space were still learning how to be. There's an edge to everything you can see, not a wall, not a barrier, just a horizon. A place where light stops arriving, where distance becomes so great that even photons traveling for billions of years haven't reached us yet. And maybe they never will. The universe is 13.8 billion years old. You'd think that means we can see 13.8 billion light years in every direction. A sphere of visibility with us at the center, simple, neat, comprehensible. But you'd be wrong. Because the universe has been expanding the whole time, since the beginning, since the moment it began. And that expansion changes everything. It stretches space itself. It pulls galaxies apart. And it means the edge of what we can see is not 13.8 billion light years away. It's 46.5 billion light years away, in every direction. That's the observable universe. The sphere of space from which light has had time to reach us. And it's so vast, so incomprehensibly large, that all the distances we've talked about so far, all the light years and galaxies and voids, are just tiny fractions of it. Let me show you what happens when distance stops making sense. The universe began 13.8 billion years ago. We call it the Big Bang, though. That name is misleading. It wasn't an explosion. Not in the way we usually think of explosions. It was an expansion, a sudden rapid stretching of space itself, from something unimaginably small to something large, and it's been expanding ever since. At first, the universe was hot, unimaginably hot, so hot that matter couldn't form, atoms couldn't exist. There were just particles, energy, chaos, a roiling sea of subatomic confusion. But it cooled, slowly. As space expanded, the temperature dropped. And after about 380,000 years, the universe cooled enough for atoms to form. Hydrogen, helium, simple elements. And for the first time, light could travel freely. Before that, photons were trapped, scattered by the dense fog of particles. But once atoms formed, the fog cleared. The universe became transparent. And the light that was released in that moment, the light from 380,000 years after the Big Bang, is still traveling, still reaching us. right now. We call it the cosmic microwave background, the CMB, and it's the oldest light in the universe, the farthest thing we can see. Not with our eyes, not with optical telescopes, but with radio telescopes, because that ancient light, once visible and bright, has been stretched by the expansion of space, redshifted, pulled into longer and longer wavelengths until it's no longer light at all. It's microwave radiation, faint, cool, barely above absolute zero. But it's there, everywhere, filling the sky, a dim glow left over from the birth of the universe. And when we measure it, when we map it, we're looking back in time. Not 2.5 million years, like Andromeda. Not 26,000 years, like the galactic center. But 13.8 billion years, almost to the beginning. And the place that light came from, the point in space where those photons were released 380,000 years after the Big Bang, is now 46.5 billion light years away. Because the space between us and that point has been expanding the whole time for 13.8 billion years. That's why the observable universe is larger than its age. Because distance isn't fixed, space itself is stretching. And the farther away something is, the faster it's moving away from us. This is hard to visualize, I know. Let me try a different way. Imagine you're standing on the surface of a balloon covered in tiny dots. Each dot is a galaxy. Now imagine someone is inflating the balloon, slowly, steadily. The surface stretches, the dots move apart. Not because they're moving through the surface, but because the surface itself is expanding. From your perspective, standing on one dot, all the other dots appear to be moving away from you. The ones close to you are moving slowly. The ones far away are moving faster. Not because they're traveling faster through space, but because there's more space between you and them, and all of that space is expanding. That's what's happening in the universe. Space itself is stretching, and the farther away a galaxy is, the faster it appears to be receding. Not because it's moving through space, but because the space between us and it is growing. And here's the brutal part, the part that breaks the dream of ever exploring the universe. About 94% of the observable universe is already unreachable. Not because it's too far, not because we don't have fast enough ships, but because it's moving away from us faster than the speed of light. Wait, faster than the speed of light. Isn't that impossible? Not quite. Nothing can move through space faster than light. That's true. Einstein was right about that. But space itself can expand as fast as it wants. There's no speed limit on the expansion of space. And if a galaxy is far enough away, the space between us and it is expanding so fast that light from that galaxy will never reach us. Not ever. Not in a trillion years. Not in infinite time. It's already gone, lost beyond the cosmic horizon. Receding into a darkness we'll never penetrate. And every year more galaxies cross that line. More light gets stretched beyond our reach. The observable universe is shrinking, not in size, but in content. Fewer and fewer galaxies remain visible, fewer and fewer stars, fewer and fewer chances to look out and see something new. In the far future, trillions of years from now, if anything still exists to look up, the sky will be almost empty, dark, silent. Just a handful of nearby galaxies bound together by gravity resisting the expansion. Everything else will be gone, pulled away by the stretching of space, lost forever. But we're not there yet. Not now. Right now, the observable universe is full, rich, bright, full of galaxies we can see, full of light that's still arriving. And one of the most remarkable things we've discovered is this. The universe looks the same in every direction. No matter where you point a telescope, you see the same structures, the same density of galaxies, the same patterns of light and dark. This suggests something profound, something almost uncomfortable. It suggests that the universe has no center, no edge, no special place. Everywhere looks like everywhere else. And if you traveled to the edge of the observable universe, to the farthest galaxy we can see, and looked around, you'd see another 46.5 billion light years in every direction. And so would someone standing there. And so would someone standing even farther out. The observable universe is not the universe. It's just the part of the universe we can see, the part from which light has had time to reach us. But the universe itself, the whole universe, might be infinite. It might go on forever, in every direction, without end. Or it might be finite, curved, looped back on itself like the surface of a sphere, so that if you traveled far enough in one direction, you'd end up back where you started. We don't know. We can't know. Not yet. Maybe not ever. Because we can only see as far as light has had time to travel. And beyond that, there's only darkness, only mystery, only the unknown. But here's what we do know. Here's what the light tells us. The universe is expanding, has been expanding for 13.8 billion years. And the expansion is accelerating, getting faster. Galaxies that are far away are receding faster and faster, pulled by something we don't fully understand, something we call dark energy. Dark energy is strange. We can't see it, can't touch it, can't detect it directly. But we know it's there because we can see its effects, the acceleration, the stretching, the way distant galaxies are being pushed farther and farther away. And dark energy makes up about 68% of the universe. More than anything else, more than matter, more than stars, more than galaxies. The universe is mostly empty space, and that empty space is full of something we don't understand. Something that's pushing everything apart. It's humbling, disorienting. To realize that the universe, we can see the stars and galaxies and nebulae, all of it, all the matter and light and structure, makes up less than 5% of the total. The rest is dark, hidden. Beyond our reach, there's dark matter too. Another mystery, another invisible thing. It doesn't emit light, doesn't interact with light, but it has gravity. We can see its effects on galaxies, on the way they spin, on the way they cluster. And from those observations, we know it's there, surrounding galaxies, holding them together, making up about 27% of the universe. So, when you add it up, when you account for everything we know, it looks like this 5% normal matter. The stuff we can see. Stars, planets, gas, dust, you mean. 27% dark matter, invisible but gravitationally active. 68% dark energy, even more invisible, pushing space apart. We live in a universe we don't understand. A universe made mostly of things we can't see, can't touch, can't explain. And the more we learn, the stranger it gets. But there's beauty in that strangeness, beauty in the not knowing, because it means the universe is still full of mysteries, still full of questions, still full of things we haven't figured out yet. And maybe that's how it should be. Maybe the universe isn't meant to be fully understood. Maybe it's meant to stay a little beyond us, a little too large, a little too strange, always just out of reach. But we keep reaching, we keep looking, we keep building bigger telescopes, better instruments, more sensitive detectors. Because even though we know we'll never see everything, even though we know 94% of the universe is already beyond our reach, we still want to see as much as we can. We want to look back to see the first stars, the first galaxies, the first light. We want to peer as close to the beginning as possible, to understand as much as we can where we came from, how we got here, what it all means. And we've come so far, so much farther than anyone thought possible. In 1920, astronomers didn't even know there were other galaxies. They thought the Milky Way was the entire universe. And then Edwin Hubble looked through a telescope and saw something extraordinary. He saw galaxies, hundreds of them, thousands, each one a Milky Way of its own, each one full of billions of stars. And then he measured their motion, and he found that they were all moving away. The farther away they were, the faster they were receding. And from that single observation, he realized the universe is expanding. That discovery made less than a century ago changed everything. It gave us the Big Bang. It gave us the age of the universe. It gave us a history, a story, a beginning. And now, with modern telescopes, we can see galaxies that are 13 billion light years away. Galaxies that formed when the universe was only 800 million years old. Young galaxies, small, chaotic, full of hot blue stars. Nothing like the mature galaxies we see nearby. We're watching the universe grow up, watching it evolve, watching stars form and die and form again, watching galaxies collide and merge and scatter, watching the structure of the cosmos unfold one photon at a time. And the light, we see the light from those distant galaxies has been traveling for so long that the galaxies themselves no longer look like that. They've aged, changed, maybe merged with others, maybe died. We'll never know, because the light showing us what they look like now hasn't reached us yet. And by the time it does, if it ever does, we'll be long gone. That's the price of distance, the cost of looking so far. You see the past, only the past, and the present, the now, is forever hidden, forever unknowable, forever just beyond the horizon. But maybe that's okay. Maybe the past is enough. To see where things began, to watch the first stars ignite, to witness the birth of galaxies, to know even just a little how the universe became what it is. Because that knowledge, that understanding is what separates us from the darkness. What makes us more than just matter drifting through space? We are the universe looking at itself, trying to understand itself. And even if we never see the whole picture, even if 94% of it slips away forever, we'll still have the memory of light, the story of stars, the quiet, patient act of witnessing. And as the universe expands, as galaxies drift farther into the unreachable dark, as light stretches and fades and finally goes silent, we stand here now in this brief moment of clarity and look as far as we can, knowing that what we see is all we'll ever have, knowing that the edge of the observable is not the edge of reality, just the edge of what light can show us. And beyond that edge, beyond the horizon, where even photons cannot return, there is still more. Still galaxies, still stars, still space, stretching on, forever perhaps, or ending somewhere we'll never know. And in that uncertainty, in that vast and quiet unknown, we find something unexpected. We've traveled far tonight, farther than any spacecraft ever built, farther than light can travel in a human lifetime. Farther perhaps than the mind was meant to go. We started with 8 minutes, the time it takes sunlight to reach Earth, a distance you could almost imagine crossing. Almost. And then we moved outward to Proxima Centauri, 24 light years away, to Oumuamua, drifting alone through the void for 300,000 years, to the Milky Way spinning slowly through a darkness 100,000 light years across, to Andromeda falling toward us across 2.5 million years of empty space, and finally to the edge of everything we can see, the observable universe, 46.5 billion light years in every direction, a sphere of light and time and ancient memory. And now, here we are, back where we started, on a small planet, orbiting a small star, in a quiet corner of a galaxy that barely notices we exist. So, what do we do with all of this? What does it mean to know these distances? To hold them even briefly in our thoughts? Maybe nothing. Maybe the universe doesn't ask anything of us. Maybe it's content to spin and expand and drift indifferent to whether we understand it or not. But I think there's something else happening here, something quieter, something that has less to do with understanding and more to do with feeling. Because when you really sit with these distances, when you let them settle into your mind, something shifts. The day-to-day shrinks a little. The worries that felt so large this morning become smaller, lighter, less urgent. Not because they don't matter, they do. Your life matters. Your struggles matter. Your joys and sorrows and small victories, they all matter. But they matter here, in this moment, on this planet, in this brief window of time we call a life. And the universe, vast and patient and utterly indifferent, reminds us of something we often forget: we are temporary, beautifully, achingly temporary. And that temporariness is not a tragedy. It's a gift. Because if we lasted forever, if our lives stretched across billions of years, would this moment matter? Would tonight matter? Would the light from distant stars feel as precious if we had infinite time to see them? I don't think so. I think part of what makes the stars beautiful is knowing we won't see them for very long, that our time here is brief, that every night we look up is a night we won't get back. And light years, these impossible distances, they teach us that. They show us scale, perspective. They show us that we are small, yes, but that smallness is not a failing. It's a feature. It's what allows us to notice, to care, to feel awe instead of boredom. Because the universe is not built for us. It's too big, too old, too empty. But we are built for it. Or at least we're built to wonder about it, to measure it, to name it, to look up at the night sky and ask quietly, softly, how far? And the answer. The real answer is not a number. It's a feeling, a sense of being part of something larger, something older, something that was here long before we arrived and will be here long after we're gone. Distance, it turns out, is not just about space. It's about time, about memory, about the light that travels for billions of years just to meet your eye for one fleeting second before it fades. And maybe that's the medicine, the healing, not in understanding the distances, but in letting them wash over you, in letting the impossibility of it all sit gently in your chest, in realizing that you don't need to hold the whole universe in your mind. You just need to hold this moment, this breath, this small, quiet awareness that you are here, now, under stars that are older than cities, older than species, older than the ground you stand on. There's a Japanese concept called mono no aware. It's hard to translate perfectly, but it means something like the pathos of things, or the awareness of impermanence. It's the bittersweet feeling you get when you notice something beautiful and in the same moment realize it won't last. The cherry blossoms that bloom for only a week, the sunset that fades too quickly, the friend you'll say goodbye to. That's what the stars give us. Mono, no aware. The awareness that all of this is fleeting. The light we see tonight left its source long ago. The galaxy we live in is slowly merging with another. The sun will die, Earth will die, even the stars themselves, those ancient beacons, will one day go dark. But for now, they shine, and we see them. And in that seeing, in that brief moment of connection across the void, there's something sacred, something worth protecting, worth remembering. You don't need to be an astronomer to feel this. You don't need a telescope. You don't even need to understand the physics. You just need to look up on a clear night, away from the city lights, and let the darkness settle around you. Let your eyes adjust. And then slowly the stars will appear, faint at first, then brighter, more and more of them, until the sky is full, crowded with light. And each one of those lights is a sun. Each one is a star. Each one is a place. And the light that touches your eye has traveled unimaginably far across distances that should make connection impossible. But it's not impossible. It's happening right now, every night. The universe is speaking to you in photons, in wavelengths of light, in ancient messages that took millions of years to deliver. And you standing there looking up are the receiver, the witness, the one who notices. That's not nothing. That's everything. There's a line from Carl Sagan that I think about often. He said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." He was right. Every atom in your body was forged in the heart of a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars that lived and died billions of years ago. Stars that exploded, scattered their matter into space, and that matter drifted, coalesced, formed new stars, new planets, and eventually you. You are made of stardust, Literally, not metaphorically, not poetically, literally. The atoms that make up your body are recycled star matter, ancient, cosmic, impossibly old. And now those atoms are arranged in such a way that they can look up, they can wonder, they can ask questions. They can measure light years and calculate orbits and dream of traveling to places they'll never reach. That's extraordinary. That's miraculous. That's the universe vast and indifferent as it is somehow becoming aware through you, through us, through this brief, fragile, temporary arrangement of matter that can think and feel and care. So maybe the distances don't need to be understood. Maybe they just need to be felt, to remind us that we are small, yes, but also connected. Part of something ancient, something vast, something that doesn't need us, but somehow in this one tiny corner of space allowed us to exist anyway. And in that existence, in this brief flash of awareness, we get to do something remarkable. We get to look back, to see where we came from, to trace the light back to its source, to ask how far, and why, and what it all means. And even if the answers are incomplete, even if the universe keeps most of its secrets, we still have this, the act of asking, the act of looking, the act of standing under a sky full of stars and feeling deeply that we are part of it, that we belong, not because we earned it, but because we're here. That's enough. That has to be enough, because the stars will keep shining. The galaxies will keep spinning. The light will keep traveling. And someday, billions of years from now, the last star will flicker and go dark. The universe will cool, expand, thin out into a cold, empty silence that lasts forever. But that's not now. Now the stars are bright, the universe is alive, and we are here to see it. So, look up. When you can. When the sky is clear. When the city lights fade. Look up and let the distances settle into you. Let them be impossible. Let them be beautiful. Let them remind you that you are small and temporary and utterly, completely lucky to be here at all. We've drifted through light and time together tonight. We've crossed distances that shouldn't be crossable. We've seen things that shouldn't be seeable. And now, as the night deepens, as the stars continue their patient work of shining across the void, I want to thank you for listening, for staying, for letting these impossible numbers and ancient lights fill your thoughts, even just for a little while. The universe is vast, lonely, empty, but you're not. You're here, you're alive, you're aware. And that awareness, that small spark of consciousness in the dark, is rarer and more precious than all the stars in the sky. So, sleep well, dream gently, and when you wake, when you step back into your life, into your smallness, remember this. The light from distant stars is still traveling, still arriving, still reaching across the impossible distances to find you. And maybe that's what light years really are. Not a measurement of space, but a reminder that even across the greatest distances, even across billions of years, connection is possible. Light finds a way, and so do we. Thank you for being here, for drifting with me through the dark. There are more stories waiting, more journeys to take, more quiet nights where the universe opens up and shows us something we've never seen before. Until then, rest. The stars will still be there when you wake, still shining, still traveling, still impossibly beautifully far. Good night,